Welcome to the fourth part of the Introduction to Haskell course, where we will go over pattern matching, Lambda functions, and function operators. Pattern matching is a useful way of defining functions in Haskell because while it is similar to conditional statements, unlike in conditional statements where we have to have an expression that evaluates to either true or false, with pattern matching, we can make those decisions based on general patterns, which don't have to be just Boolean values. So they can still be direct values, which means it could be even Boolean values. But we can also use general argument patterns, which we'll explore a bit later. And these prove to be very useful when working with Haskell functions. So, like guarded equations, the patterns are evaluated from top to bottom, which means the first one that matches from the top is going to be evaluated further, or the function body associated with that pattern will be evaluated. And here, from our previous video, we're going to take the card color function that we defined with a case of expression and use pattern matching this time to define it. So to define a function with pattern matching, at the top we have the type signature, and then we list the patterns from top to bottom. For each of the patterns, we state the function name first. So the first pattern in this case will be a direct value of a string, which is hearts, and in that case we return red. The second one is diamonds, we also return red. Spades and clubs, we return black. The last pattern we have here is the wildcard, which matches any pattern, any value, or any pattern in general. And in that case, since we already checked the patterns that we're interested in, we just return the default, not familiar with this card suit. Okay, so card color works the same way as before. If we give it diamonds, we get back red, and if we give it something other than our 4 patterns, then we get back the default message. That was an example using patterns of mostly direct values, except for the wildcard character, to use pattern matching. But when we start working with tuples and lists, the data structures, then pattern matching can be much more useful. So we'll start here with tuples, and tuple patterns are a combination of 2 things. First, the patterns of individual elements in the tuple. Okay, so this could be like direct values of each of the elements in the tuple that we use for the pattern, or just more general patterns for each of the elements. But in any case, we can create patterns for each of the individual elements. And 2 is the length of the tuple. So the length of the tuple itself comprises the full tuple pattern, because as we know, tuples cannot be infinite. They have to have a finite number of elements in them. So each tuple will have an exact number of elements, and so the pattern of a tuple of arity of 2 and 3 is of course not the same. Here's an example for 2 functions, one that returns a card suit and one that returns a card rank for a given card, under the assumption that we represent a card as a tuple of 2 strings. So the first one is a suit and the second one is the rank. So let's look at pattern matching here. We have getSuit, the name of the function, and then we have a pattern which is in parentheses signifies it is a tuple, and then the first argument, or the first element of this tuple, we name it suit, and the second element we just use the wildcard character. So wildcard character in this case is used to simply ignore the second element. it still means that there is a second element there. It just means that we don't care about what the element actually is. It's important that there is an element, because otherwise it's not a tuple of two elements that we need for this function. But what the actual value is, we don't care, because we are just going to return the suit, which is the first element of the tuple. So here we see a more general pattern being used to define a function. And the same way for getRank, we use the same assumption that the card is represented by this tuple of two strings. And in this case, we ignore the first element, which is the card suit, because we don't care about it. And we name the second element rank, and then we just return the rank. So if we use this function to get suit of a card that's ace of hearts, then we get back the suit, which is hearts. And if we try to get the rank, we get back the rank, which is ace. Now let's take a look at list patterns, which are a combination of, again, the patterns of the individual elements in the list and the length of the list as well. But with lists in Haskell, we can have infinite lists. However, we can still use a length of a list in a pattern, which we'll see in this example here. So we want to write a function that checks whether a list of any type has exactly 4 elements. So we write the type signature, we call the function check4, and then we use the type variable a without any class constraint. So it's a completely polymorphic type. Any type is valid for this function, and it returns a boolean. So the boolean will be either true or false if it contains 4 elements or if it doesn't. So how do we use pattern matching to define this function? We have the function name here, and then we define our pattern that satisfies our goal for the function, which is we want a list of 4 elements. So in this case, we use 4 wildcard characters, because we don't care about the values of the elements at all. We are just checking the length of the list. So we define the pattern as a list with square brackets and then 4 elements inside it. What the elements are, we don't care, so we use wildcard characters, and that's it. So you can see this is a general pattern that can work with many different lists. So we can have a list of integers, for example, 1, 2, 3, 4. It satisfies this. A list of 2, 3, 4, 5 also satisfies this pattern. A list of strings, a list of characters, and so on. Any list that has 4 elements will satisfy it. And in that case, we return true. In any other case, which is so because patterns are evaluated from top to bottom, so we first check that it has 4 elements, and if it doesn't, then we know we are going to return false. Then we can just use the wildcard character, because we say whatever else it is, we will return false. So notice the difference between the wildcard here and the wildcard inside the list pattern above. So the wildcard stands for the same thing, right? It matches any pattern. So the wildcard inside the list matches any pattern of the first element of the list. But the wildcard character in the false version of this function is a pattern of the list that's being accepted, actually. So because the scope is different, right? So check4 receives 1 argument. In that case, the argument is here the list, and in this case the argument is a wildcard character, which is also a list, which we know from the type signature. But in this case, a wildcard represents a full list, so a pattern of any other list that doesn't contain 4 elements. So depending on the scope, on where the wildcard character is placed, it can represent different things. But in any case, it means that it matches any pattern. Now we'll go back to the cons operator, the list constructor. which we can also use in list patterns, and it is often used when working with lists. So just a reminder of how the cons constructor works is to rewrite this check for function instead of the list pattern that we had, to rewrite it with the cons constructor. So we know that a list is actually constructed using the cons operator. So to replace the pattern from the last slide with the cons, we can wrap it in parentheses, because this is a function application, right? So we have to wrap it to represent one argument. And then we have our 4 wildcard characters, and at the end we join it with the empty list, which is as we know how lists are constructed, right? So this pattern and the previous pattern is the same thing. It's 4 elements, whatever they are, joined together in a list. So 4 elements combined mean the list has 4 elements. We evaluate the true. Anything else we evaluate the false. And here you can see that the function works correctly. So a list of 3 elements is false, a list of 4 elements is true. Now we're at a point where we can introduce this general pattern, which is very commonly used in Haskell for list. And this pattern can represent any list with at least one element. So X will be that one element, or the first element of the list, and cons XS will be everything else in the list. This is what the pattern means. So X is the first element of this list, and XS is everything else. In other words, X is the head and XS is the tail. So we saw the functions head and tail that return these things respectively. So head returns the first element of the list, and tail returns all the other elements except the first one from the list. This XS in this case can therefore be a list of multiple elements. So if we have a list of, for example, 1, 2, 3, if we apply this pattern to it, then X will be 1 and XS will be 2, 3, a list of 2, 3. Okay, it could also be an empty list, of course, because we know that lists are constructed at the end with a cons to an empty list. So once we get to the end of the list, or imagine that we have a list of just one element and that element is 1, then this pattern will match that list as X is 1 and XS is just an empty list. So if we have 1 cons empty list, then that is equal to a list of 1. Right. X and XS are commonly used names for the list head and tail. And this pattern enables us to match against list with an undefined number of elements. In other words, when we use this pattern, we don't really know how many elements XS has, and we don't really care because we are creating patterns, right? So this will become very important when we get to recursion in Haskell, and that will be in part 5 of the series. Since we mentioned the functions head and tail that we saw before, we can now actually look at their definitions and understand them, because in the prelude they are actually defined exactly using this pattern of X and XS. So head uses this pattern, takes the first element X and then cons, and then instead of calling it XS here, it just uses the wildcard character, because again it doesn't care about this argument. This wildcard still represents the tail of the list, but the value is not stored in a variable because it's not going to be used. Head only returns the first element. On the other hand, tail, which returns the tail of the list, is going to ignore the first element of the list and just return XS, which is the tail. So this pattern holds true for any list with at least one element, as we saw, because if we So these are actually not complete definitions of head and tail, because they each have another definition for the case of an empty list. This is not really important now, but if we try to use head on an empty list, we will, this case just throws an exception or an error, and the same for tail, because an empty list does not have a first element and does not really have a tail. It's just an empty list, so this makes sense. That's it for the introduction to pattern matching, and now we get into Lambda functions. So Lambda functions are anonymous or nameless functions, in other words, and they can be applied without an explicit declaration. So what we did so far was have a function, we define it with a name, with a function body, and so on. And with Lambda functions, they operate just like normal functions, and even how we define them is similar, but we don't use a name for them. We, instead of a name, we just put this backslash, which is supposed to represent the Lambda symbol, right? So we just use the backslash and we list its arguments. It can have multiple arguments, so arguments 1 and 2, and then instead of the equation sign, we have the right arrow that points to the function body. Okay, so it can be used as any other function. So here we have an example where the function is wrapped in parentheses because we need to scope it if we want to apply it to this argument. And so this code line says there's a Lambda function here. It takes one argument x and it returns x times 3. And in this case, it's of course already applied to the number 4. So it's applied without an explicit declaration of the function first as a nameless function. Lambda functions are used when we need a function, but we're only going to use it locally. So it's only going to be used in another function, and we don't need to declare it. We're not going to use it again. Okay, so just to show how we could use a Lambda function in actual code, here's the track score example using a Lambda function this time to, instead of calculating the score in each of the if cases, we just have the score variable defined as a local definition, and it's calculated with a Lambda function. This is actually a silly example because we could just apply this function abs, which stands for absolute. So if the number is negative, it will be turned to positive. So absolute of -3 is 3, and absolute of 3 is still just 3. We could just apply it to time minus average time. But just to illustrate how Lambda functions work, here we have a Lambda function that accepts 2 arguments. It returns the function abs applied to the difference between those 2 arguments, and then here we apply it to our 2 arguments. So since this function, the function body abs x minus y, we will really use inside this track score function. We don't need to define it in another place and give it a name and so on. We can just use it as a Lambda function without a name. Now we're getting to the last part of this presentation where we'll look at function operators. So function operators are used to improve code readability pretty much. We can write Haskell code without them, but as we saw, a lot of the times we have to wrap things in parentheses in Haskell to give it explicit scope and to sort of give the order of function applications. So with function operators, we can reduce the number of parentheses needed. And also, as we'll see, we usually use them when we apply multiple functions to the same arguments. We'll see that on the next slide. But for now, here's an example of a function which is not using function operators, but just to illustrate what we want this function to do. So we wanted to take a number, square it, and then check whether whether the number squared is greater than 100. Okay, so we can do this by combining two functions, right? The first one is square, which will lift the number to the power of 2, and the second one will just check if that result is greater than 100. So if we write these two functions combined, we would write it like this. It accepts one argument, and we square the number first. That's why we put the parentheses here. So we lift the x to the power of 2, and then we check whether the result of this function application square is greater than 100. So now let's look at the actual function operators, their definitions, and then we'll see how to use them in an example. So the first one we're going to look at is the function composition operator, which is the dot. Here it is wrapped in parentheses to signify it's a function, but when we actually use it, we can just use the dot, as we'll see a bit later. So this is the definition of the function composition operator. It takes in two functions. Usually function arguments in Haskell are called f, g, and so on, as in mathematics. And these two arguments are then, it is defined here as a lambda function. So the result of the function composition operator is another function, in this case defined as a lambda function. And this result function takes in an argument x and returns f and g applied to x in a specific order. So it associates to the right, meaning that the function g on the right will be applied first to x, and then f, the function on the left, will be applied secondly to the result of the first function application. So we see that it composes two functions into one. So this is actually one function, as we see, because it's composed of two, and applies them both to an argument, in this case x. As I said, this associates to the right, so the function on the right is applied first. That's basically the function composition operator, and the second one is the function application operator. It is represented by the $, and the prelude definition is f $x is simply fx. So it takes in a function, it takes in an argument, and applies the function to the argument. Now this may seem a bit silly. I mean, why do I need this $x when I can just write fx? Yes, but as we'll see, the $, the function application operator, is a so-called lowest priority operator. So it means it will try to evaluate what's on its sides first, and only then apply the function. So now let's look at how to define our square GT100 function using function operators to reduce the number of parentheses. We can define it as a function that takes in one argument, still the x, and then what we want to do is apply square to x first, and then GT100 to the result of that first function application. So we know we can compose these functions with the composition operator, which will first apply the function on the right, square, and then the GT100 to the result of the first function application. We then use the function operator, function application operator, the $, to apply this composition to x. So why does this work? Or you may wonder why. So since the function composition operator, function application operator, the $, applies a function on the left to the argument on the right, why doesn't it apply square to x and then try to compose with GT100, which would not work because of type issues. In any case, the answer is, as I said, that function application operator is lowest priority operator. So the function composition, the dot, has a higher priority, so it will be evaluated first, and these two functions will be composed before the application takes place. So these two functions composed will return another function, and then that function will be applied with the $sign to x. So that's why we can get rid of the parentheses here. Because let's look at another example. If we wanted to write this function with just function composition and without the function application operator, then of course we can still do it, because we don't have to use function operators at all, or we can use just the ones we choose. Well, all of it is fine, but it has different syntax. So in this case, we still take the argument x, we compose the two functions, and we want to apply them to x. But in this case, we have to wrap this function composition together to say, okay, first compose these functions and then apply them to x, because otherwise square will be applied to x first and then composed with g, which won't work because of type, of course. And so yeah, without the function application, we still have to scope things with parentheses to tell Haskell what to do first and how to apply things in which order. In either case, so we can see that the function works fine. If we give it 9, so the 9 squared is 81, which is less than 100, and 11 squared is 121, which is more than 100. So in this case we return true, and in the case of 9 we return false. That's the end of this presentational part, where we looked at pattern matching, Lambda functions, and function operators. And now let's go into the practical part, where we'll try to use these concepts in our Haskell code. Let's start with some examples of pattern matching. So we mentioned that we can use pattern matching with literal values. Let's start with that. So if we imagine a function that takes an integer and just returns another integer, we can match on the literal values of the integer argument. So for example, we can define, if we get the integer 0, then we'll return 1. If we get the integer 1, we'll return 5. We get 2, we'll return 10, and anything else we will return 0. So this is an example of pattern matching on literal values. And if we open up GHCI and load our session 4 module here, then if we apply the function to 5, we get 0. If we apply to 1, we get 5. So we see that it works as is defined based on the literal values. And besides literal values, we can also use it for general patterns, which are most useful with tuples and lists. So we saw this very common list pattern of x representing the head of the list and xs representing the tail of the list. And besides using pattern matching in function definitions, we can also use it in expressions, so such as where and let-in definitions. So we can define y here as not a function that takes in an argument, but just an integer. So we can define things as not just functions. So the double colon in Haskell refers to as a type signature. So if it is a function, it's a function type signature, but in this case it's just the type of this variable y. And because we will define y as equal to, let's say, x plus 5, and then where does x come from? We define where so we can use a pattern here, and we'll say x, and let's ignore the tail of the list, so we will take the head, and this pattern will be equal to, for example, now we apply some functions to a list. let's say reverse this list of 1, 2, 3. And so how does this read? So y is an integer, because after evaluating all of this, we will get back an integer, right? So we have here the pattern for the where definition, which is x representing the head of this list being reverse of 1, 2, 3, and then the actual function body just adds 5 to the x. Okay, so if we evaluate y now, it will always be 8, because there is no argument that this function takes. It's just a value. It's always the same. It is a result of some function applications, but the value is always 8, because this list is static and the number we add to it is static. So after reversing, the head of the list will be 3, and that's what's added to 5. We can also write this, call this y1. We can also write with a let in expression. So y1 in that case would be, so let x, and the tail we can ignore, be equal to the reverse of this 1, 2, 3 list in the expression x plus 5. And if we reload this again and we use y1, it's 8 as well. So these two are equivalent, just one is using the where and one is using let in. Okay, so this is the general list pattern that we can use, XXS. And in this example, we are using pattern matching on expressions and not function definitions, which is also valid. The next thing we mentioned in the presentation were the Lambda functions, which are anonymous or nameless functions in Haskell, which work the same way as other functions, except they are not defined with a name and are used only locally. And we can apply them directly instead of defining a function and then applying it. So let's write a function swap. So the type signature of this function is going to be, it's going to swap the places of a tuple. It's going to accept a tuple of type A and type A, and it's going to return the same type, and it's just going to swap the positions around. So we can define this with a Lambda function. So we define swap as a Lambda function. We use the backslash, and we list the arguments now. So in our case, we accept a tuple argument, and we're going to pattern match here. So we can use pattern matching in Lambda functions as well, and we're going to call the arguments x and y. I mean the elements of the tuple x and y. And this function is going, so in Lambda functions, instead of the equation sign, we use the right arrow, and what we're going to return in this Lambda function body is just y and x reversed. Right, so of course this is a bit of a silly example, because we don't need to use a Lambda function for this. Of course, the suggestion here is, why not just define it normally? But okay, this is just an example for Lambda functions. So this should still work fine. And if we take a tuple of 1 and 2, we get back a tuple of 2 and 1. Right, so one thing to notice here is that here in the swap, we don't list the argument, which is okay. Because we don't actually apply the argument here in the function body, right? We just define the function body as another function. So this is sometimes used in Haskell, and this is equivalent to actually saying what are we going to call the tuple? Let's call it A, and then we have this Lambda function. In this case, we have to wrap it in parentheses, and then we apply it to A. So if we reload this, it's the same thing. right? So this works if we list the argument or if we don't list it. It's kind of, I think it's called ETA reduction. I saw different names for it, but it's basically like in math, if you have the same thing on both sides of the equation, you can just negate them with each other. So we can basically just shorten this definition by removing the argument. We can also remove the brackets in that case. And now this function definition is just the function that's going to do the swapping once it receives the argument. The last concept we talked about in the presentation were function operators for function composition and function application, the dot and the dollar sign. So we can explore the type of these functions or operators, starting with the dot. So we get 3 arguments, 1, 2, and 3, to produce a final result, which is of type C. Okay, so we got 1, and this is a function argument, right? It has an arrow inside it, so it means this argument is a function that takes in an argument of type B and returns an argument of type C. That's the first function, the first function on the left. Then the second argument is a function that takes in an argument of type A, returns a type B, and finally this composition operator accepts an argument A. So what does this mean? As we saw in the presentation, we compose 2 functions together and we apply the one that's on the right side first. So in this case, that's this function. So we basically apply this function from A to B to this argument A, and then we get B as a result. And then we apply the first function, the one on the left, which takes in the exact type returned from the function on the right, type B, and we return the result type C. So these 2 functions are composed, and then when we apply to A goes to this function, which returns a B, then B goes to this function, which returns a C, and that's the final result of the composed function. Right, so here every type is has its own type variable, which means they could be different types, but they could be the same type as well, since we have no restrictions. So A here could be the same type as B and C, but they could all be different types as well. This is what the annotation means when it's using different type variable names. And the function application operator simply takes in a function and the argument that of type that the function is supposed to accept and applies the function to give back the result B. And this one is a bit simple. Okay, so we can take an example. For example, let's say we have a list and we want to get the last 2 elements of the list. Okay, so we can call this function last2. We will accept a list of some type A and we'll return the same type, so a list of type A, except we'll return only the last 2 elements. So let's use XS. We don't need to pattern match in this case, because so what we want to do is take the last 2 elements. So how can we do that? Well, we can reverse the list and then use the take function to take 2. So we can compose those two functions and apply it to XS. Now we know that in function composition, the function on the right is applied first, which is the order of application is important as well. So when I write function composition functions, I tend to write them from the right to the left, if that makes sense. So what I want to do in this case is I first want to apply the reverse function. So I write that function first. So I want to reverse it, and then I write what I want to do next on the left side. So after I reverse the function here, I want to take 2 from from that reversed list. And then we can apply this to XS. Now, as we see, we have XS again on both sides. So I'm using here the function operator for application to write this without any parentheses, but I can also just remove that altogether, and like in this example, I can define last2 as just a function that when it gets the XS argument, it's going to apply what's on the right to it. So, but for now, we'll keep it explicit with the function application. And if we reload this and we use last2 on this 1, 2, 3, 4, let's say, list, then we get back 4 and 3. So we get the last two arguments, but they are in reversed order. If we wanted to get them in the order that they were initially, we can compose actually another reverse here. So after we have our two elements taken, then we can reverse them again. Reverse. And in this case, we'll get back the 3, 4, which is the correct order that it was at the start. Now let's go do some katas as usual. And I picked some katas out for this session. I try to pick katas that allow us to make solutions that using things that we just learned in the presentation, but it's not always so easy. So sometimes we'll just practice things we learned from before, and sometimes we'll practice exactly what we learned, and sometimes we'll even encounter some things that we didn't mention in the presentation. But in any case, it's good practice. So we can start with this one, cats and shelves. The description is there is an infinite number of shelves, one above the other, and there's a cat. And the cat can jump either 1 or 3 shelves at a time. So from shelf I, it can jump to I plus 1 or I plus 3. It cannot climb the one directly above his head, which would be I plus 2. So that's not allowed. This is the illustration. So from 1 to 2 is okay, from 1 to 4 is okay, from 1 to 3 is not okay. So we'll get the input as a start and finish shelf numbers. So the cat doesn't always start at 1. It can start at 5, for example, and then it can the finish number will be the number of shelf above the starting position. It will always be positive integers, and finish will always be small. Finish will always be higher than the start, no smaller than the start. So our task is to find the minimum number of jumps from start to finish. Here is an example. Start is 1, finish is 5. The answer is 2, because first it can jump to 4. First it can jump to 4 using the 2 shelf jump, and then to 5 with an additional jump, or it can first jump to 2 and then to 5. It doesn't really matter. Okay, so how can we solve this? This is the starting point that we have, and type signature is a bit different. We didn't see before this word type. In Haskell, the word type is an unsigned integral type with the same size as int. So it's the same as int, except it's unsigned, which means it cannot hold negative numbers. So it's basically has the same memory as int, but because we know we're not going to get negative numbers, it can hold numbers that are greater than just int, but they have to be positive numbers. In this case, we can just consider it an integer number. We don't need to worry about the unsigned, but it is defined as a word. Okay, so we know we're getting 2 arguments, the start and the finish. And what we need to do is calculate the minimum number of jumps. So basically the most effective way to jump. So what we can first do is calculate the difference that we need to jump, right? So in our definition, we can define diff as the finish minus the start, since we know that finish will always be greater than start. And then we'll get, so difference will be the number of shelves we actually have to jump. Then what we can do is let's try to use as many as we can of the I+3 jumps, since those are the most efficient, right? So if we take our difference and divide it by 3, we'll get the number of those jumps. So that can be our first thing, and then the rest will have to be filled with jumps of 1. But in any case, we can divide, so we use the div function, difference divided by 3. This is our number of jumps. So for example, in this case, where start is 1, finish is 5, the difference is 4. We have to jump 4 shelves, right? So if we divide 4 by 3, we get 1. We can do 1 big jump of 2 shelves, but it's not perfect division, right? It has a remainder, because 5 divided by 3 is 1. 4 divided by 3 is 1, but 1 is left over. So we still have 1 shelf to jump. So besides this, we need to add that remainder, which, if you remember, we can just get with the modulo operator. So if we divide difference and get the remainder with the mod, then that's exactly what we want. So in this case, if we apply it to this example, 4 divided by 3 will be 1, and plus diff 4, so 4 modulo 3 is also 1. So we get 1 big jump and 1 small jump, which is 2 jumps, and that's the most effective way to get to this solution. So that's this kata done here. There are, of course, probably many different ways to do it, but I am choosing this one here and consider this one done. So let's go to the next one, which will be this one, descending order. In this kata, your task is to make a function that can take any non-negative integer and return it with its digits in descending order. Essentially rearrange the digits to create the highest possible number, right? So you have an input with 5 digits, and we need to sort them in a descending order. So same for these other examples. Okay, so what we would like to do is take this number, this integer number that we're gonna get, and sort its digits. So an integer is not a list type, we cannot sort it, but a string is, right? A string is a list of characters. So what we could do here is, if we could turn this integer into a string, then sort that string in the order that we want to, in descending order, and then read it again as an integer to turn it back into an integer, then that would be our solution. Okay, so we'll have an integer here, call it a or x. And okay, so as I mentioned, there is like an order of functions we would like to apply, right? So we can use function composition here. First, we want to transfer the integer to a string, and we already encountered this before. There is a function called show, which takes a value and returns its string representation. So if we apply show to x, then this is the first step. We now have the string of the integer that we received. Okay, so what next? Next, we want to sort it. So we can compose a function for sorting it. And now, how do we sort a list? Well, there are many ways, but it would be convenient if a function already exists, right? And it does. but we need to import it from the module data.list. And we can, when we do imports, we can also specify exactly what we want to import. So in this case, we want to import this function called sort, and this will sort the list in ascending order. Okay, so let's sort it. Now we have our string representation of x sorted in ascending order. So what we want to do is reverse it so that it's descending order. So we can compose another function reverse to do that. And then we actually have our number that we want to have as the result, but it's in the wrong type. It's a string type still. So this is something we haven't seen before, but there is a function just like show for going from an integer to a string. There is also a read function, which we'll get into a bit later in the course as well. But read is basically the opposite. It reads a string and casts it to appropriate type. So it can read different types, such as even Boolean values. It can read true and turn it into a Boolean. It can read an integer string and turn it into an integer. It can read floats and so on. But basically that's the last thing we want to do, right? So if we have a suggestion from the editor to ETA reduce, right? So like we said, we don't really need x here since it's on both sides. This function can be just defined as the function composition of these 4 functions. So let's try it. We load from Katas descending order, and we can take an example here. So descending order of this number is now an integer whose digits are sorted in a descending order, right? Same for this example, and so on. The next one is maskify, and in this kata we need to maskify the credit card number. So okay, the description, blah blah blah. You have to write the function which changes all but the last 4 characters into the hash symbol. Okay, so we get a string. Okay, we get a string and we have to return a string that masks all the characters except the last 4. Okay, if we get a short string, then we return this. If we get an empty string, we return an empty string. Okay, here are some examples. So the last 4 is 4 characters are not masked, the rest are masked. So even if it's exclamation point, for example, any character, the last 4 we just don't mask and the rest we mask. Okay, so how can we solve this? We accept a string, we call it XS, and what we want to do is basically replicate the hash symbols, right? A certain amount of times. Now, how many hash symbols do we need? We need basically the length of the list minus 4, and that's it, right? That's how many hash symbols we need, and then we just need the last 4 of the list. So how can we get that many hash symbols? So we know we're going to use replicate, and we're going to use length. Okay, so let's use length and first apply it to XS. That's the number of characters the string has. Now, what we want to do is then after we get the length, we want to subtract 4 from it, right? And there is a function in Haskell, subtract, which subtracts a number. So we subtract 4. Then we have the number of hash symbols that we want to replicate. So we just need to combine it with, compose it with replicate at the end. Okay. So what does this mean? We take the length of SS, we subtract 4 from it, and then we replicate. We apply replicate to the result of length minus 4. But we know that replicate takes in 2 arguments, right? One is the number of replications we want, and the second one is what we want to replicate. So the second one will be the hash symbol that we want to replicate. Okay, now we basically have this part, right? We're going to replicate hash symbols for a certain amount of times, and to this list we need to add the last 4 characters. How can we add the last 4 characters? Well, we could use something that we used in session 4, which is like last 2, and then we reverse and take and so on. But this is a bit too much. There is actually a simpler way, because we know besides the take function we have the drop function, which drops the first the number of elements that we select from the start of the list, so, and returns the rest, right? So, and the rest is what we're interested in. So we can drop. Now, how many elements do we want to drop? Well, it's the same number of elements as this, right? It's still the length of the list minus 4. That's how many we want to drop. Okay, so we can do the same thing except without replicate. Subtract 4 length of SXS. Okay, and we apply this to XS. That looks okay, I think. Let's see if we can load from Katas Maskify, and we use Maskify on this Batman example. Yeah, okay. We get the correct thing. What we notice is that we have some code duplication here, right? Subtract 4 length of XS, subtract 4 length of XS here. So I'm not going to fix it, but in general, what I would do is write a local definition for this so that it's not calculated twice, but instead just calculated once here, and then change the function body a little bit to use this local definitions instead. I encourage you to try and do it. And we'll move to the next one, which is remove the minimum. Okay, remove the minimum, the Museum of Incredible Dull Things. We have exhibitions with a rating, and we need to remove the one with the lowest rating. However, just okay, so she asks us to write a program. Okay, we have a task. We have an array of integers. We need to remove the smallest value. Do not mutate the original array or list. Well, in Haskell we cannot mutate even if we want to. If there are multiple elements with the same value, remove the one with the lower index. Okay, so we always remove one. If they are the same value, we don't remove all of them, just one with the lowest index. If you get an empty array or list, you get it back as empty. Do not change the order. Okay, input 1, 2, 3, 4, 5. 1 is removed. 5, 4, 3, 2. 1, 4. 1 is removed, and here 1 is removed, but the second one is not removed. Okay. So we could solve this in some very creative way, probably, but this is one of the things where you stop and think, like, there must be a function for this, right? And there is. It's called delete. It is also in the data.list module, I think. Yeah. And this function actually does exactly what we want to do. So it takes two arguments. One is the value that we want to remove from the list, and the second is the list. So here, since we want to remove the minimum value, we first need to find the minimum. So the minimum, and then apply it to XS, and then once we have that minimum, we can compose it with the delete function, and then then delete is applied to the minimum of XS, which is its first argument, and then we need to still apply it to XS. So then delete is applied to, for example, here we find the minimum 1, and then we apply delete to 1 and this full list to get back this result. So this should be okay. Remove the minimum, remove smallest, and we have a list of 1, 2, 5. We remove the 1, and also let's check this one. So we have to make sure that we remove only the delete works in a way that it deletes the first element encountered that has the same value. So it basically goes 2 is not 1, 2 is not 1, then 1 is 1. Okay, I delete, and that's it, function done. So this is what we should get, and this is what we do get. So that's remove the minimum done. Now let's go to this one, string ends with. This is a simple kata. It says complete the solution so that it returns true if the first argument, which is a string, ends with the second argument, which is also a string. So we get first the some string, and then we get another string, and we need to check that the first string ends with the same characters as the full second string. So this is true, and this is false because it does not end with D, and instead ends with C. Okay, how can we do this? So we have two strings. Basically, we know that something is going to have to be, if we call the strings XS and YS, we know that we have to compare something with YS, right? Because it has to be equal to YS. So what exactly has to be equal to YS? So what we want to do is look at the end of the first string. The thing is, the second string can be of varying length, right? It can have 2 characters, 1 character, any number of characters. It's not defined. So the length of the ending of the first string that we want to look at will depend on the length of YS. So we know we want to drop a certain number of elements from the first string so that all we are left with is the part that equals the number of elements in the second string, right? So we know we're going to use drop, right? We're going to drop a certain amount of elements, and we're going to drop that from XS. So now we just need to find out the amount of elements we want to drop. So how do we calculate that? We can just look at these examples. So here we have a length of 3 and a length of 2. And what we want to look at is the last 2 elements. So we need to drop 1, right? 3 minus 1 to get the last 2. So we need to drop 1, which is 3 minus 2, right? So we can just take the length of XS and subtract the length of YS. Yeah, and then we will get equal string lengths. We drop the extra amount of elements from the beginning, and we get back, when we drop that from XS, we get back the ending that we need to compare with exactly YS. So load Katas string ends with solution, and so we get ABC and BC. In the example is true, ABC and D is false. Okay, we can make our own example as well. Whatever, we can have a bunch of elements here and a bunch of let's say Ignacio should be true, this ends with this is false. Okay, so it seems to be working fine. Okay, moving on to the last kata for this session. It's called the sum of sequence, and your task is to write a function which returns the sum of a sequence of integers, where the sequence is defined as 3 non-negative values: begin, end, and step. If begin value is greater than the end, your function should return 0. Okay? If end is not the result of an integer number of steps, then don't add it to the sum. Okay. 2, 2, 2 is 2. Right, so it's beginning, end, and step. And so this would result in a list of just 2, and the sum is 2. 2, 6, 2 would be 2, 4, 6, right? Okay, so the sum is 12. 1, 5, 1 is 1, 2, 3, 4, 5, 15. 1, 5, 3 is 1, 4, and that's it. So the sum is 5. Okay, so the list we want to look at is, for sure, we can define it as we saw with some of the example list functions. We had begin, and then we can define the step, but we don't define the step with a number, but instead we add the step to the begin argument here. So we are using pattern matching here for this tuple of integers. We call the first element begin, the second end, and the third step. And then the rest we fill, and it's going to be filled with this step that we defined here until the end. Also, we know that this function, this list composition is not going to include the end unless it's so if end is not the result of an integer number of steps, it shouldn't be included, and this is exactly how this works, so we don't have to worry about that. So this is our function, this is our list, and basically we just need to calculate the sum of this list, right? Sum all the elements, which is the sum method or function, and that's it. So it does say something about if beginning value is greater than the end, your function should return 0. I don't know if we actually need to worry about this, if this is defined this way. I think not. But if we do, we can just write if, if begin is greater than end, then we return 0, else we return our function definition, right? So try to load this from Katas, sum of sequence, and sequence sum of a tuple 2, 2, and 2 is 2. From the examples, 2, 6, 2 is 12. 1, 1, 5, 1 is 15. And 1, 5, 3 is 5. So it seems to be working fine. Of course, to make sure you run it in the Code Wars website where there's extra tests, and but yeah, I'm pretty confident this is it's a way of writing the right solution. There are surely more actually more creative ways and probably more efficient ways than this, but from what we know, this works. Okay, that's the last kata for this session. Thank you for watching, and I'll see you in the next video.